Yeah, you have any doubts from previous week or this week's content?
Yes, sir, related to this convex set, like
Okay.
how to identify convex set and like what exactly are the properties of convex sets.
Yeah. So, like, if S is a convex set, the definition is clear to you.
Yes, sir, that is clear.
So, if you have some x1 comma x2 in S, then S is convex if for all x1 comma x2 in S, uh, lambda x1 plus 1 minus lambda x2 is also in S, where lambda is in 0 to 1. Okay, so if it satisfies this property, then it is a convex set.
Okay, sir, but how to visualize this? Like, I have particularly that particular problem because equation is fine. I got it, but how to visualize like this particular set is going to be a convex set or
So visualization you can only do in 2D and at the max in 3D, right?
yes. Mhm.
So basically, you have some set and you take any point, and what like this is x1 x2. What this basically tells is any point which is between them on the line joining between them, that is also a part of that set. So this is convex. So in this circle case, it is true. Like any point you take wherever, any 2 points you take, if you draw a line joining them, all the points will be part of that set only. But
Okay,
if
got it.
but if I have something like this, if this is my set, then if I take this point and this point here, and I take the line joining them, then these all points are not part of the set, right?
Okay, perfect.
So that is the basic idea of that convex sets. Yeah.
Okay, sir, got it.
Okay. Any other doubt?
No, sir, that was one of the thing that's
Okay. So then maybe we can solve some questions from this week. Mm, where is that? Yeah. So let me close this. So if I have a optimization problem of this form, so I subject to a1 x equal to b1, a2 x equal to a2 x plus b2 y less than equal to small b2, and y less than equal to, okay, then question is asking, uh, write this in the standard form. So write above in standard form. Okay. So standard form is something that we define for a LP, right? So first of all, is this a linear program?
yes, sir. Yes.
Right. This is a linear program. And what is the standard form?
It should not have any inequality.
Uh, it has one inequality, right?
Yeah, this should not have in the standard form.
I mean, in standard form also there is one type of inequality
Mm.
constraint.
Okay.
You want to construct in standard form something which is like C transpose X. This is your objective, and Ax equal to B and x greater than equal to 0. So this part is there, no?
Yes.
So this one we want all our variables to be positive. Okay. So how do we do it in this thing? So we have this equality constraint is there, but we don't have x positive thing. There is this inequality constraint, and we have these inequality constraints also. So we need to get rid of those. So I think first easy thing we can do is make this into an equality constraint. So to get an inequality constraint, like convert inequality to equality, we add a
Slack
slack
variable.
slack variables. So we get a2x plus b2y plus z equal to b2, and z is greater than equal to 0, right? So this is done, and we got a new variable which is also positive. Now let's take care of this part, the upper bound and lower bound on y. So to do that, we will add some slack and some surplus variables. So y less than equal to u, for that we can add y plus some s1 is equal to u. Okay, and s1 is greater than equal to 0. And for this part, what we can do is y minus s1 is equal to l, right? And s1 is greater than equal to 0. Sorry, s2. This is s1, this is s2. Okay.
So can we do it like u minus y is greater than 0?
Sorry, can you repeat?
Can we do it like upper bound minus y greater than or equal to 0?
Upper bound minus y. Upper bound minus y greater than equal to 0. No, at the end you want equality constraints, right?
Okay, we want equal. Yes, yes, got it.
So here we converted this to equality constraints, and the surplus and slack variables. So this is slack variable, this is a surplus variable. Both are greater than 0. Now the only problem that we have is we don't have y greater than 0 and x greater than 0. So how do we take care of that? We need to create some new variables which can be positive, and some their linear combination should be equal to x.
If u minus v equals to 1, something like that.
Yeah. So you can write x as some x plus minus some x minus, right? Any real number can be written as the difference of two positive real numbers. Similarly, where x plus greater than equal to, like x plus comma x minus are greater than equal to 0, and similarly y also we can write as y plus minus y minus, or y plus x are greater than equal to 0. So then we just need to rewrite these two parts. It will be a1 x plus minus x minus equal to b1, a2 x plus minus x minus plus b2 y plus minus y minus plus z equal to, and these also we will have to write y plus minus y minus plus s1 equal to u, y plus minus y minus minus s2 equal to l. So now all our variables x plus x minus greater than equal to 0, y plus y minus greater than equal to 0, s1 s2 greater than equal to 0. And what else is there? And the objective will be maximize x comma y c transpose x plus minus x minus plus b transpose y plus y minus. Okay, so then like you can convert it into some matrix form appropriately and write it like this, and that is quite straightforward. So originally we had all the variables in, like the x will be vector, y will be vector. So we had, let's say this was m1 dimension and this was m2 dimension. So we had m1 plus m2 variables. Now here we have uh, this is m1, m1, m2. So here I have x plus y plus x minus y minus s1 s2, and this will also be m2, right? So I have 2m1 plus 4m2 variables, and I converted into standard form. Oh, plus z also. Z is also z. So z dimension can be something different. Let's say n dimensional. So this is n plus n. So it's quite much more than what we had over in our in the other form. And the number of constraints, if you see, it is here you have these extra constraints. These inequality constraints are more. The number of constraints is also more in the standard form. Okay. do some other question. Any doubts in this?
No, that's great.
Okay. Uh, okay, let's do this question. Suppose my S is x, that x1 plus 2x2 greater than equal to 2 and minus x1 plus x2 equal to 4 x1 x2 greater than equal to 0. Okay, we want to find the extreme points of this. What are its extreme points? So it's two dimensional, so we can simply draw it. So this is say x1 x2 and so x1 x2 are greater than 0, so I only need the positive part of the axis. And how do I draw x1 plus 2x2 greater than equal to 2? So I need to draw this line. So I put x1 equal to 0, I get x2 equal to 1, putting this as 1. And if I put x2 equal to 0, I get x1 as
2.
2. So it will be a line passing through this and it is greater than equal to 2. So if I substitute 0 comma 0 here, I get 0 is greater than equal to 2, which is wrong. So I want all points in this direction. This is my feasible region, right? Basically, this part is not there because this x1 and x2 should be greater than 0. So I have this area. Now I want to plot this. This is a equality. So it will pass through x2 equal to 4. Oh, sorry, 1, 2, 3, 4 somewhere here, I think. And x1, I put x2 equal to 0, I get x1 equal to minus 4. So it will be somewhere over there. Let me shift this plot. Let me put it somewhere. Try to align it. Okay. So 4 minus 4. So it's an inequality constraint, so all my points are on this line, right? And this part is not really my feasible region, and the inequality only holds on this. So all the points x1 x2 greater than 0 on this line basically. So what is the extreme point?
There will be only one.
One extreme point, right? And that is this point, 0 comma 4. What if I remove this constraint?
The equality constraint.
Yeah, the
Then
inequality. X1 plus
will
2x2 greater than equal to 2.
then we'll have two.
If I remove this,
The first one or the second one?
the first,
The first one. Okay. Then also we'll have one
we'll have 1, right? So why is that?
because x2 is greater than zero.
Yeah, that is correct. So why is it that by removing this, my extreme point is not changing, or my feasible region itself is not changing?
Because of the equality constraint.
Yes, partially, because I this could have been something like this also, right?
Yes.
So if I remove, if would I removed this one, then my extreme point would have changed.
Got it.
But there is one reason, there is one property because of which I'm able to remove that. So the reason is, I think, mm, I can get this constraint by the other constraints, or rather, I can get the first constraint by a linear combination of these two. So if I do minus x1 plus x2 equal to 4 plus 3x1 greater than equal to 0, plus 3x2 greater than equal to 0, then I get 2x1 plus 4x2 greater than equal to 4, right? So it is x1 plus 2x2 greater than equal to 2, right? So if I add these three constraints, I get the first constraint. So it's a linear combination of the other constraints. So it's in some sense redundant. Am I clear?
Yes, sir.
Okay. So if I had drawn something like here, let's say x1 greater than equal to 2. So that will be a line here, right? This you can't get by a linear combination of the others. So that's why that will change your feasible region, but this constraint is not changing my feasible region. If I draw anything like this also, that also you will be able to get by a linear combination of the other constraints. So that is not cutting my feasible region. It is a valid inequality. Okay.
Yes, I got it.
One second. So let's do some other question. If you have a set C Ax x such that Ax less than equal to 0 and is m cross n, then what is the max number of extreme points for C? Any guess?
A is a full rank matrix.
Whatever be the case.
M minus n. Yes.
M minus n.
Yes. I was solving a similar question. That's why I'm just creating an analog.
M minus n you are saying. So you are assuming m is greater than n, no?
Yes.
Yeah, that is an upper bound. M minus n is an upper bound for this answer, but it's not a strict upper bound. So here the number is even more less. So here there is this thing given, right? A special case when Ax is less than equal to 0. So what will be the nature of the this inequality? Like you have a set
Hyper.
hyperplanes, yeah. So you there's a set of hyperplanes, na Ax equal to 0.
Yes, yes, get on it.
So what is the property of hyperplanes which have ax equal to 0?
I agree.
So you want an extreme point. An extreme point is what? It's a vertex, right? Vertex of your polyhedra. So this vertex means what? It's an intersection of the hyperplane. So if my x is in Rm, intersection of at least m hyperplanes is needed to create a vertex, right? If I am in 2D, then I need at least two lines to create a vertex. If I am in 3D, then I need like three lines at least to get a vertex, right? I need three lines to create a vertex. So in this, if ax equal to 0, then what is a point through which the hyperplanes pass through? Common point. That vertex is a solution to many hyperplanes, right?
That will be origin.
Yes. So origin, all the hyperplanes pass through the origin, correct?
Yes. So there will be only one extreme point.
Maximum one.
Okay.
There can be a case where all your planes are this only, right? All your hyperplanes are like a1x1 plus a2x2 less than 0 and some ka1 x1 plus ka2. If it is of this form, then is the same hyperplane that you get. So in this case, there are zero extreme points. But at max, if you add one more a different hyperplane, then it will only intersect origin. How many ever you add, all will intersect origin only. They won't have any independent rows of A. They will intersect at origin only. So at max, you will have one, right? At max, only one. It's clear, right?
Yes, sir.
Okay. Mm, extreme rays was also taught. Now, what will be the extreme ray for this question, this set?
There will be only one.
Only one, right?
Yes.
And it will be, how did we write the extreme ray? What will be, how will we write that extreme ray? Will be something in this direction, right?
Hmm. Yes.
So it can be something like D is 1 comma 2. Is that how it will be? No, sorry, 1 comma 1. So if I add any point 0, 4 plus k 1 comma 1, it should satisfy it. So and k is greater than 0, any x. So if I put substitute this here, what do I get? X will be uh, minus 0 plus k plus 4 plus k. So this k and k will get cancelled. I'll get 4. So all of this will satisfy this. Okay.
Can you sir repeat this once, please?
So if this d is my direction, my
Okay.
extreme ray, so any point of the form x equal to, and let's say this x, this is x1, this is my extreme point, right?
Yes, sir.
So x1 plus kd will always belong to s for all k greater than equal to 0, and x1 is 0 comma 4 and k is 1 comma 1. So I substituted this point in my second inequality, then I get this.
Okay, got it.
I should not reach x1, x1 is already here, no? So I wrote some xe. So this is what extreme this is an extreme ray. here we talked about extreme point. Let me take some other question. If D is a, like I have some problem as some set Ax equal to B, S is equal to, then if D is extreme ray, then is AD equal to 0. Okay, like we need to prove this basically. D is extreme ray, then AD is equal to 0.
It will satisfy the equation because it is going to be there in the boundary.
What can you repeat?
It will satisfy the equation because it is going to be there in the constraint boundaries.
Yeah, how do we show?
No idea.
Just we need to use the definition, right? If D is a, you don't even need extreme. If D is a ray of S, so what is the definition of D? That I take any x plus mu D that is also in S. If x is in S for mu greater than equal to 0, right? That is the definition of ray. So that means Ax plus mu D is equal to B, and Ax, because x is in S, Ax is equal to B, which implies I have B plus mu AD is equal to B. This B cancelled, and this mu is a scalar. So I have mu AD equal to 0,
Ready.
AD is equal to 0. Okay. So for all extreme rays, like all ray basically, not even extreme, all rays will satisfy this. So if Ax less than B was there, S equal to like this, then all rays of S will satisfy what condition?
This AD equals to 0.
No, I have this right.
Okay, let's make it.
So if D is array, if D is array, then AX plus new D should be less than equal to B. So I have AX plus mu AD is less than equal to B. So I can take this over there, B minus AX. Now AX is less than equal to B, that implies B minus AX is greater than equal to 0.
So AD is less than equal to 0.
Sorry?
AD will be less than or equal to 0.
We can't directly show that, right? Because this just says this. If this was less than equal to 0, then we could have said. But this is greater than equal to 0.
Got it.
So then how do we show? So this is true for all x. This is true for all x, right? All
Yes.
x in S. I mean this. Both basically. True for all x in S. So we can take some x star such that B minus AX is equal to 0. X star. And this x star I can substitute in this back. So I get mu AD is then equal to 0. Okay.
That is applicable for X star only, right?
Yeah, so this x star, if I substitute in this, that means AD is less than equal to 0, right?
Okay.
So it will satisfy for, if AD is less than equal to 0, then it will satisfy for all x, right? Whatever x here, because this is always greater than equal to 0. You got it?
Yeah, yeah.
Okay. So what do we need now? So this we are done. Question. Can we show that xbxn, this is a basic feasible solution? Then it is an extreme point. Okay, you got what is the question?
Yes, sir.
So if we have a basic feasible solution of this form, then we need to show that it is an extreme point. Remember what is the definition of basic feasible solution? I think it was there in the last part of the video. Were you able to watch it? I just write it again. So if you have C transpose X such that Ax equal to Bx greater than equal to 0, and A is full rank, full row rank. Okay, A is Rm cross n. So A is full row rank means we can get, this implies we can get M linearly independent rows or columns, right?
Yeah.
So that means we can separate A as in some form, B and
And
yeah, yeah, this B is M cross M, N is M cross N minus M. Okay, we took the M columns, uh, M linearly independent columns of A. Okay, we took M linearly independent columns of A and we guided them as B, and the remaining we put them as N. Is clear, right?
yes, sir.
So this bn now ax equal to b, you can write as bn xb xn is equal to b. Okay, these are the
Yes.
variables which get multiplied with b. These are the variables which get multiplied with n. So basic, so what they do is they set xn equal to 0. That means if I do nxn, I get 0. So if you multiply these two, what you'll get is bxb plus nxn equal to b, and you put all xn equal to 0. So then you get that xn equal to 0. You get bxb equal to b, and because this has b inverse exists. Why? Because of this. So xb you can write as b inverse b. So this is, so this xb equal to b inverse b0 is a solution, right?
Yes.
Is a solution to ax equal to b, right? But for it to be feasible, we need x greater than equal to 0. Feasible to this. This is a solution only to ax equal to b. The solution to ax equal to b, and if b inverse b is greater than equal to 0, implies xn is greater than equal to 0. Then it is uh, so this is called a basic solution, called basic solution. Okay, then it is a basic feasible solution. You got this?
Yes, sir.
Yeah. So this is how you define a basic feasible solution. So then this, what we are saying is, if it is a basic feasible solution, then it is an extreme point. That means if it is of this form and b inverse b is greater than 0, then it is a extreme point. We need to prove that. So how do we show if we have some point x? So when is it a extreme point? Like what is the definition? Let's say the set defined by this is S. So what is the definition of extreme point? X is extreme point of S if for x1 x2 in S, x equal to if for any x1 x2 in S, x equal to such that x equal to lambda x1 plus 1 minus lambda x2 implies that x1 equal to x2 is equal to x. Okay, that is the definition of extreme point. Is it clear?
Yes, sir.
So you can't write it as a convex combination of any other point. Basically, it is a convex combination of itself.
Yes, got it.
So we need to show that this basic feasible solution is a convex combination of itself. Okay, so we take x equal to b inverse b0, and let's say we have x1 x2 in S such that lambda x1 plus 1 minus lambda x2 is equal to x. So we're basically saying b inverse b0 is equal to lambda x1 comma b, let's say x1 comma n. So this x1 again I can split it into the basic part and non-basic part, and 1 minus lambda x2 basic x2 n. Okay, so we need to show if this is an extreme point, that means this x1b should be equal to b inverse b, x2b should also be equal to b inverse b, and x1 and x2n should also be equal to 0. So this part we can check first. 0 equal to lambda x1 n x1 comma n plus 1 minus lambda x2 comma n, and lambda is in 0 comma 1, and because x1 x2 belong to s, that implies x1 comma x2 is greater than equal to 0, right? So this whole quantity is greater than equal to 0 because this is positive, all are positive. So that means, that must mean what? x1 comma n is equal to x2 comma n is equal to 0, right? Is clear?
Yes, sir.
So now what we have is,
B versus
yeah, this part we need to show. So we know that x1 is in s, so that implies this x1 b comma 0 is also in s, right? And that is in s implies, if I multiply it by b n x1 b0, this should be greater than equal to b, that is my constraint, right? Or equal to b, equal to b. So that means bx1 b is equal to b, so x1 b is equal to b inverse b. Same we can show for, same true for x2b. So we have shown that x1 x2 both are of this form only. So it is an extreme point. Equal to x. Is it clear?
yes, yes.
Okay. What else can be discussed? Just looking at this book. Okay, there are some questions in the back that can be discussed.
So can you explain how to like what is the basic difference between polytop and polyhedron? Like I got this idea that they one is bounded, other is not,
Hmm.
but I'm not able to know
Yeah.
visualize that how it will be like different.
So polyhedron is a intersection of half spaces, right? So
Yes.
basically, this is there. This is a half space, and another I take. This is a half space. So this region is a polyhedron, intersection of these two half spaces.
And there is a condition like this half space should be finite.
Yeah. So there are only two half spaces, no?
Yeah, no. For example, if I take a circle, then it won't be a polyhedron.
Yeah, because circle is an intersection of
Infinitely.
infinitely many half spaces.
Okay.
And polytope means if I take one more this, then this region, there is a polytope because now it is bounded. I have a I have boundary around this, right? For,
Okay. Got
for the
it.
previous one, I didn't have a boundary because it can be anywhere. It is unbounded in this direction. Other way you can say is for a polytope, the direction set is empty. The ray set of rays is empty.
Okay. Got it.
Okay. Let me ask one question. If I have, say, minimize C transpose X such that A transpose X is less than equal to B. Okay, A is vector. C, A, B all are in Rn. X is also in Rn. Then what is the solution to this? So into so the solution is of this form. Solution is of the form x star is equal to lambda b if c is equal to a lambda for lambda greater than equal to 0 in minus infinity otherwise. So we have only uh, one inequality, no set. So this is a half space basically, and whereas the solution is of this form. So what does it mean? Okay, so if c is equal to a lambda and lambda is greater than equal to 0. That means uh, if let's say this was A transpose X less than B is this line, C transpose lambda is a, like C transpose X will be a line parallel to this, right? Depending on C.
Okay, so either it will be lambda times this constraint, or it will be infinite. It won't exist.
Yeah. I mean we want to find X such that it lies on this. Okay, this is not X star. This is the optimal value. F star is on this one. Sorry. What did I do? F star is on this one, not X. So what is happening is if I put C equal to A lambda, I get lambda A transpose X, and the maximum value that A transpose X takes is B. So I'll get lambda B. And if C is not equal to A lambda, and yeah, so this lambda should be greater than 0 for this to be the max, right? If lambda is less than 0, then I can take X equal to some very negative value. Basically, whatever is the negative part of like here somewhere, such that I get a very negative value. Okay, wait. Okay, this should be max, I think. Or if I can keep this as main, and this should be less than equal to 0. And here I am saying, yeah, wait. So C is equal to A lambda means C transpose X is equal to lambda A transpose X is equal to lambda B. Like this is the minimum value it can get when lambda is less than 0. You're clear? if C is not equal to A lambda, that means this hyperplane is not really parallel to this. Like C transpose X equal to some F, it won't be parallel to this. So I can change F such that it can go anywhere. So I can change F to make it minus infinity. Is it clear?
Yes, sir.
Okay, let me take this question. If I have minimize ax minus b infinity right above as an LP. Okay, so they're asking if I have this objective, then write this objective as a linear program. Okay, you know what this infinity norm means?
No, sir.
So V is a vector of some k dimension, then V infinity is max k V V max I V I. Okay, where I is 2 k. Got it? The dimension of V with the maximum value, that is the infinity norm. So V was 2560, then infinity norm of V is 6, so 6 as the max value. Is it clear?
Yes.
So we need to write a linear program such that by solving that linear program I get the solution to this objective. Okay, so we need some objective and some constraints which are linear. Now whatever our objective is, let's say we minimize some objective and we get F. Now this F is the uh, infinity norm of some ax minus b, right? Yeah, one more thing is it is the max of the mod value. That's I forgot. Sorry, the max of the modulus of this. So if I had v equal to minus 2, 5, 6, and then minus 10, then v infinity is will be equal to 10 because the absolute value of this is maximum. So basically what we can say from this is each value of v will be less than equal to it's v infinity, right?
Okay, yeah.
Minus v infinity, right? So that means we can write ax minus b is less than equal to, instead of f5 let me write some t. Okay, now this t is what we need to minimize. So I can write t here, right? So this t is multiplied by some vector of ones, that we can say v infinity into one vector. Okay, this one vector is a vector of ones because this is a vector now. So does will minimizing this achieve this? So we can check whether, let's say, t minimizes this. Say there is some t star. Let's call this 2. Let's call this 1. T star minimizes 2. So I need to check whether t star minimizes 1 also. So t star minimizes 2 means I know ax minus b is less than equal to ax minus b is less than equal to t star and minus t star. Okay, and let's say there is some, say, t t hat minimizes 1. So t hat will also satisfy this. But there will be one constraint such that ax minus b ith value is equal to t hat, right? For some I. The what is this? So if ax minus b I is less than equal to, like if it is less than t star, then I could have still minimized t star, right? I could have used t hat because t hat is a solution to, t hat is feasible in one also. Sorry, in two also, because it satisfies this constraint. Okay. So t hat is greater than equal to t star, and from this you will get that t hat is less than equal to t star. That means t hat should be equal to t star. Is it clear?
Yes, sir.
Yeah, I think that is it. Any other doubts that you want to ask? This vector one I dropped, but it's there implicitly here as well. I think we need to join later for these all the questions that we discussed together.
I'm sorry, thanks, but sorry, could not join it earlier. I will just go through this again sometime. Thanks.
Meanwhile, if you have any doubt in that, you can ask.
Yeah, I will. Thanks.
Okay, then there are no doubts. Then we can close the session. So these questions, whatever I discussed, they were from one is from this exercises, the exercises in the second chapter of non-linear programming by Vazara, and this is chapter fourth chapter of convex optimization by Lloyd. Okay. the questions are there only. Okay, then if there is no questions, then I'll close the session.
Thanks, man.
Yeah, if you have any doubts, you can post in the
Yeah, yeah.
discussion forum also, or you can email me also.